Energy forms the foundation of modern existence, driving everything from illuminating bustling cities to fueling industrial manufacturing and supporting advanced technological infrastructure. For more than 100 years, the world has relied heavily on coal, oil, and natural gas as primary energy sources. These resources provide stability, but carry severe consequences. Carbon dioxide emissions, climate change, air pollution, and significant risks to public health and well-being. Renewable energy options, such as wind, solar, and hydroelectric power, are increasingly viewed as viable replacements. Yet they come with inherent drawbacks. Their output hinges on unpredictable weather conditions, making consistent energy supply challenging. A wind farm, for instance, can produce hundreds of megawatts of electricity when conditions are optimal, but its output plummets when winds are faint or inconsistent. Similarly, solar panels operate effectively during daylight hours, but lose nearly all functionality under cloudy skies or at night. At the same time, global energy demand is surging at an unprecedented rate. Data centers powering artificial intelligence, high-tech manufacturing facilities, and electrified transportation networks all require a steady, large-scale, and reliable electricity supply. The critical question is not merely about having enough electricity, but ensuring that electricity is clean, safe, and consistently available to meet these growing needs. Confronted with the dual challenge of sustaining economic growth while drastically reducing harmful emissions, the world is urgently seeking innovative solutions. This is where next-generation nuclear technology, specifically small modular reactors, steps into the spotlight. These advanced systems are increasingly seen as a vital component, offering a transformative approach to achieving a sustainable, reliable, and environmentally friendly energy future. While traditional nuclear power plants are often associated with colossal structures, costs soaring to tens of billions of dollars, and construction timelines stretching beyond 10 years, small modular reactors known as SMRs introduce a completely different paradigm. As their name suggests, the key difference lies in their compact size and innovative design. An SMR facility can fit within an area comparable to a single football field, a stark contrast to the sprawling nuclear complexes that once occupied hundreds of acres of land. This reduced footprint does not mean diminished capacity. A standard SMR can generate between 50 and 300 megawatts of electricity, enough to power a small city, an industrial zone, or a large-scale data center critical for modern technology. The second groundbreaking feature is modularity. Instead of building the entire facility on site, the core components of SMRs are prefabricated in controlled factory environments with rigorous quality assurance processes. These pre-built modules are then transported to the installation site and assembled like interlocking building blocks. This approach dramatically shortens construction timelines, reduces the risk of project delays, and mitigates cost overruns, persistent issues that have haunted the nuclear industry for decades. Energy providers can start with a single reactor and scale up by adding more modules as energy needs grow. Similar to how data centers expand by integrating additional server units, SMRs are also designed with superior safety features. Many models incorporate passive safety systems that operate using natural physical principles, such as gravity, convection, or atmospheric pressure. Rather than relying entirely on electric pumps or complex mechanical equipment, this design reduces the likelihood of accidents and enhances the reactor's ability to remain stable during emergency situations. With lower heat generation and moderate fuel requirements, SMRs also significantly minimize the risk of reactor core meltdowns, a concern that often fuels public apprehension about nuclear energy. Beyond electricity production, SMRs offer remarkable versatility across a range of applications. They can supply steam for chemical manufacturing plants, oil refineries, or material production facilities, provide heat for urban heating networks, and even support seawater desalination to produce fresh water in regions facing water scarcity. This adaptability makes SMRs an appealing solution for countries with diverse energy demands, from sustaining industrial operations to improving living standards for communities. Another key advantage is their flexible deployment. Thanks to their compact size and optimized safety protocols, SMRs can be installed closer to energy consumption hubs, rather than in remote, isolated locations. This proximity reduces electricity, transmission costs, and enables cities, industrial parks, or even remote islands to access reliable, on-site energy sources, enhancing energy security and efficiency. The emergence of SMRs is reshaping how we view nuclear power. If traditional nuclear plants are akin to the bulky mainframes of the information technology world, SMRs are the compact, flexible, and scalable servers of the energy sector. This transformation marks the dawn of a new era, where nuclear energy can integrate seamlessly into power systems, working in harmony with renewable energy sources to build a sustainable, low-carbon electricity grid for the future. China is swiftly emerging as a trailblazer in transforming small modular reactors known as SMRs from visionary concepts into tangible, operational realities. For many decades, the majority of nuclear energy projects were concentrated in nations like the United States, France, and Russia. However, China has now taken the lead by rapidly deploying advanced technologies that many other countries have only progressed to the design phase. Two flagship projects exemplifying this remarkable advancement are the HTR-PM and the Ling showcasing China's bold strides in nuclear innovation. The HTR-PM, situated in Shandong province, holds the distinction of being the world's first commercially operational fourth-generation, high-temperature, gas-cooled reactor. Unlike traditional nuclear reactors that rely on water for cooling, the HTR-PM utilizes helium, an inert gas, to efficiently transfer heat. Each individual module of the system generates a capacity of 105 megawatts of electricity, and when two modules are combined, the total output reaches approximately 210 megawatts. This substantial capacity is sufficient to provide stable, reliable electricity to more than 1 million residents. The successful commercial operation of the HTR-PM marks a historic milestone. It represents the first time a fourth-generation nuclear technology has been fully implemented in practical use on a global scale. Similarly, the Ling, also known as ACP-100, located on Hainan Island, stands as the first land-based commercial small modular reactor to receive approval from the International Atomic Energy Agency. With a generating capacity of 125 megawatts, the Ling can supply electricity to approximately 500,000 households. However, its significance extends far beyond power generation. The reactor's versatility enables it to provide heat for urban heating systems, produce steam for industrial applications, and, most notably, support seawater desalination, a critical necessity in Hainan, where freshwater resources are scarce, capable of converting seawater into tens of thousands of cubic meters of fresh water each day. The Ling demonstrates that SMRs are not merely sources of electricity, but also multifaceted infrastructure solutions addressing diverse needs. What sets China apart is the extraordinary speed and expansive scale of its deployment efforts. While some small modular reactor projects in the United States or Europe remain mired in the regulatory approval process, China has already brought next-generation reactors into full commercial operation. The Chinese government has set ambitious targets to deploy numerous SMRs across the nation, with a particular focus on industrial cities and coastal regions facing freshwater shortages. This vision extends beyond domestic boundaries. China also aspires to export SMRs, positioning them as a strategic component of its clean energy technology portfolio to serve developing nations worldwide. These advancements highlight China's strategic positioning in the global nuclear energy race. Once a nation reliant on imported nuclear technology, China now independently designs, manufactures, and deploys cutting-edge reactors. Through small modular reactors, the country not only meets its enormous domestic energy demands, but also establishes a powerful new tool for energy diplomacy, solidifying its stature as a leading powerhouse in nuclear technology innovation. Finland, a nation located in the far northern reaches of Europe, is widely recognized for its prolonged and severe winter seasons. In many parts of the country, winter temperatures regularly plummet below 0 degrees Fahrenheit, making heating an absolute priority in the nation's energy strategy. In the capital city of Helsinki, more than 90% of the heat required for residential and commercial use is supplied through centralized district heating systems. These systems primarily rely on power plants fueled by coal, natural gas, or oil, which generate considerable carbon dioxide emissions. With Finland's ambitious goal to achieve carbon neutrality by the year 2035, finding sustainable and eco-friendly alternatives to the current heating infrastructure has become an urgent necessity for the nation. This pressing need has driven Finnish scientists and businesses to explore small modular reactors, specifically the innovative LDR-50, or low-temperature district heating reactor. Unlike traditional large-scale nuclear reactors designed primarily for electricity generation, the LDR-50 is meticulously engineered to provide heat directly to urban district heating networks. With a thermal output of approximately 50 megawatts, a single LDR-50 reactor can deliver sufficient energy to keep tens of thousands of households warm and comfortable during Finland's harsh and extended winter months. A key advantage of the LDR-50 is its low-pressure operation combined with advanced passive safety systems. In the event of a power failure or technical malfunction, the reactor is capable of cooling itself without the need for complex mechanical pumps or external intervention. This feature is critical for securing approval from local governments and communities to construct reactors in close proximity to residential areas. Furthermore, the LDR-50's compact design allows the entire facility to be built underground. Leveraging Finland's dense granite bedrock as a natural protective shield, this innovative approach not only reduces construction costs significantly, but also enhances safety by eliminating the need for the massive concrete containment domes typically associated with conventional nuclear power plants. For Finland, the primary value of small modular reactors lies not in electricity production, but in their potential to replace coal and gas-powered plants in the heating sector. Decarbonizing heating systems is a far more challenging task than decarbonizing electricity generation. Yet it constitutes a substantial portion of the country's overall carbon emissions. By integrating SMRs into district heating networks, Finland can drastically reduce carbon dioxide emissions while ensuring that residents have access to a consistent and reliable heat supply throughout the long, frigid winter season. This initiative highlights Finland's practical and tailored approach to energy innovation. Rather than adopting the large-scale energy models of global superpowers, Finland focuses on addressing its specific need, providing clean, sustainable heating for urban populations. If successful, the LDR-50 could not only help Finland meet its climate objectives, but also serve as a pioneering model for other European cities grappling with the challenge of phasing out coal and gas from their heating systems. With plans to implement small modular reactors in the coming years, Finland is demonstrating that next-generation nuclear technology is not exclusive to densely populated or heavily industrialized nations. It can play a vital and practical role even in a small nation with a steadfast commitment to combating climate change and building a sustainable future. China and Finland are charting distinct courses in their adoption of small modular reactors. Yet both nations view these innovative reactors as pivotal technology for constructing sustainable energy systems. A comparison between the two countries vividly illustrates the extraordinary flexibility and immense potential of SMRs, which can be customized to address vastly different national priorities and challenges. In China, the primary focus is on delivering stable, large-scale electrical power. With a population surpassing 1 billion, 400 million individuals, and a robust heavy industrial economy, China demands an energy source that is both environmentally clean and sufficiently powerful to support its continuous economic expansion. Projects such as the HTR-PM and the Ling one exemplify this strategic direction. The HTR-PM, boasting a capacity of 210 megawatts, and the Ling one, with 125 megawatts, underscore China's commitment to reliable electricity production. Beyond generating power, China integrates additional capabilities, such as seawater desalination and industrial steam production, into these projects. This approach simultaneously tackles multiple pressing issues: shortages of fresh water, the need for industrial heat and manufacturing processes, and the rising electricity demands of urban populations. This comprehensive, multi-purpose strategy optimizes both economic benefits and societal advancements from a single nuclear initiative. Conversely, Finland's priority is not centered on vast electricity output, but on addressing a unique challenge: providing heat during its harsh winter months. With district heating systems supplying up to 90% of the heating needs for residents in the capital city of Helsinki, transitioning from coal and natural gas to SMRs offers a direct path to reducing carbon emissions in a critical sector. The LDR-50, or low-temperature district heating reactor, with a thermal capacity of approximately 50 megawatts, is precisely designed for this purpose. Compact in size, equipped with advanced passive safety systems, operating at low pressure, and constructed underground. The LDR-50 represents a meticulously crafted solution tailored to the specific requirements of this Nordic nation. The comparison highlights how each country capitalizes on its distinct strengths. China leverages SMRs as a cornerstone of its ambitious industrial and technological agenda, demonstrating its capacity for large-scale manufacturing, rapid project deployment, and aspirations to export this technology globally. In contrast, Finland adopts a localized and pragmatic approach, focusing on addressing community-driven needs and advancing its climate objectives. One nation emphasizes global influence and scale, while the other prioritizes practical, region-specific adaptation. This divergence underscores the fundamental strength of SMRs, their remarkable adaptability and versatility. The technology is not limited to a single, rigid framework. It can serve as a robust electricity solution for a densely populated nation, while also providing clean, reliable heat for a small urban community. This level of flexibility is a feat that traditional energy sources struggle to accomplish. From a global perspective, China and Finland demonstrate that small modular reactors are not merely theoretical concepts, but are actively being implemented in diverse, practical ways. Both nations, united in their pursuit of carbon reduction, affirm that SMRs have the potential to become a transformative tool, strategically redefining the global energy landscape for the 21st century. Although small modular reactors are seen as a promising solution for clean energy systems, the path to making this technology widespread is fraught with obstacles. These challenges are not solely technical, but also encompass economic, legal, and societal trust issues. The first major hurdle is the initial investment cost. One of the most significant promises of small modular reactors is cost reduction through mass production in factories. However, during the early stages of deployment, costs remain high. To achieve economies of scale, a substantial number of reactors must be built consistently. This creates a difficult cycle to break. Nations want lower costs but hesitate to invest without clear evidence of economic viability. Governments and financial institutions must step in to provide initial momentum, paving the way for stronger private sector involvement. Next is the issue of legal frameworks and safety regulations. Most nuclear laws and licensing processes worldwide were designed for large reactors with capacities in the gigawatt range. When applied to small modular reactors, which operate at just a few dozen to a few hundred megawatts, many regulations become outdated or overly cumbersome, leading to complex and time-consuming procedures. Some countries have begun discussions to adapt these frameworks, but progress is uneven. The lack of consistent global standards could further delay commercialization, particularly for nations seeking to import or collaborate on this technology. Radioactive waste management remains a long-term challenge. Although small modular reactors produce less waste than their larger counterparts, safe storage solutions for tens of thousands of years are still necessary. Some innovative designs aim to reuse spent fuel, reducing both the volume and hazard level of waste, but this technology is not yet widely implemented. Deep geological storage projects, such as those in Finland, show a viable path forward. But more countries need to adopt similar approaches to establish a global standard. Equally critical is public trust. In the collective memory, incidents like the Chernobyl disaster of 1986 or the Fukushima accident of 2011 linger as enduring concerns. Despite the superior safety designs of small modular reactors, the public often views the nuclear industry with skepticism. Developers must prioritize transparent communication, clearly explaining safety mechanisms, climate benefits, and risk management strategies. Only when society feels confident will these projects gain widespread support. These challenges are not insurmountable. In fact, openly acknowledging these limitations is a vital step toward maturing the technology. Initial investments, regulatory reforms, effective waste management, and fostering public confidence will determine how quickly small modular reactors can transition from experimental projects to becoming a cornerstone of the global energy system. The development of small modular reactors extends far beyond China and Finland. On a global scale, a new race is unfolding, where nations and major energy corporations are fiercely competing to establish leadership in next-generation nuclear technology. In the United States, numerous energy technology companies are investing heavily in small modular reactors. designs such as the NuScale Power Module, with a capacity of 77 megawatts per reactor, and the TerraPower Natrium project, backed by Bill Gates, are garnering significant attention. However, many projects face hurdles related to high costs and complex regulatory processes. The greatest challenge for the United States is streamlining licensing procedures while demonstrating economic viability to compete with coal, natural gas, and inexpensive renewable energy sources. In Canada, provinces like Ontario and Saskatchewan are collaborating to develop small modular reactors to support both the electrical grid and the mining industry. Canada aims to construct its first SMRs before the year 2030, viewing them as a solution to gradually replace coal plants and facilitate resource extraction in remote regions. In Europe, beyond Finland, countries like the United Kingdom and France are also advancing their own SMR programs. The United Kingdom has announced plans to develop the Rolls-Royce SMR, a design with a capacity of 470 megawatts, targeting deployment within this decade. France, a nation with a strong tradition in nuclear power, sees small modular reactors as a means to maintain its leadership while progressively modernizing its aging reactor fleet. According to data, more than 70 small modular reactor designs are currently under research or licensing worldwide, with capacities ranging from a few dozen to several hundred megawatts. Some models are so compact they can power a small town, while larger ones can directly replace coal or gas plants. This trend paves the way for flexible power grids, where SMRs complement renewable energy sources and ensure a continuous supply. Beyond electricity, many nations anticipate that small modular reactors will play a vital role in energy security and international technological competition. Exporting SMRs could emerge as a new form of energy diplomacy, akin to the export of liquefied natural gas or solar panels. China is poised to introduce its Ling Long one to the global market, while the United States and Europe are working diligently to refine regulatory frameworks to avoid falling behind. The race for small modular reactors clearly reflects a shift in global energy thinking. Instead of relying solely on massive, costly nuclear projects, countries are seeking compact, scalable, and rapidly deployable solutions. The nation or entity that first proves the cost-effectiveness and safety of SMRs will gain a significant advantage in the energy market of the 21st century. The emergence of small modular reactors is boldly carving out a transformative new phase for the nuclear energy industry. The standout strength of this cutting-edge technology lies not only in its compact, space-efficient design or its remarkable ability to be constructed rapidly, but also in its groundbreaking capacity to expand the applications of nuclear power into realms that were previously overlooked or underutilized. From generating reliable electricity to supplying heat for urban communities, powering heavy industrial processes, desalinating seawater for water-scarce regions, and even producing clean hydrogen to fuel the energy transition, small modular reactors introduce a revolutionary paradigm of flexibility, adaptability, and innovation in the global energy sector. One of the most critical advantages of small modular reactors is their ability to provide unwavering 24-hour, 7-day-a-week operational stability. Unlike renewable energy sources, which depend heavily on variable conditions such as wind speed or sunlight availability, these reactors operate continuously, delivering a consistent and uninterrupted power supply. This reliability positions them as an ideal complementary partner for other clean energy sources, such as solar or wind, helping to maintain balance, stability, and dependability within electrical grids. In regions experiencing rapid expansion of technological infrastructure such as sprawling data centers, advanced semiconductor manufacturing plants, or large-scale industrial complexes, the ability to deliver stable, reliable electricity is just as valuable as achieving cost efficiency, if not more so. Beyond their impressive technical merits, small modular reactors carry profound strategic significance on the global stage. Nations that take the lead in mastering and deploying this technology early stand to gain a substantial competitive advantage that could shape their influence for decades to come. Exporting small modular reactors not only generates significant economic revenue, but also serves as a powerful tool for energy diplomacy, fostering international partnerships and enhancing a country's global standing. A vibrant global market is steadily taking shape, where diverse reactor designs compete fiercely on critical factors such as cost-effectiveness, stringent safety standards, and practical applicability across various contexts. However, the path to widespread adoption of small modular reactors is not without its challenges. The costs associated with large-scale production must be reduced over time to make the technology economically viable. Regulatory frameworks need to be carefully revised and adapted to ensure safety, compliance, and public confidence. Additionally, the management of radioactive waste remains a complex issue that demands innovative, long-term solutions. Yet, these obstacles are sparking unprecedented collaboration among governments, private industries, and the scientific community. By sharing expertise, prioritizing transparency in operations, and engaging in clear, honest communication with the public, stakeholders can build the trust necessary to secure broad acceptance of small modular reactors. When viewed from a broader perspective, the rise of small modular reactors represents a fundamental shift in how humanity approaches nuclear energy. Once regarded as an expensive, niche technology reserved exclusively for massive, centralized power plants, nuclear energy is now being reimagined as a versatile, adaptable tool capable of serving a wide range of contexts. Whether powering bustling metropolitan cities, remote islands cut off from traditional grids, or specialized industrial zones with unique energy demands, small modular reactors have the potential to deliver clean, stable, and sustainable energy solutions tailored to diverse needs. A new era of nuclear energy is dawning, one that does not seek to replace existing energy sources entirely but rather to complement them, offering a practical and forward-thinking pathway toward a low-carbon economy. When integrated with renewable energy sources like solar, wind, or hydropower, small modular reactors can serve as a foundational pillar, ensuring the sustainability, security, and long-term resilience of global energy grids. Through this powerful synergy, the vision of a clean, reliable, and highly adaptable energy system for the 21st century is gradually becoming a tangible reality. What are your thoughts on this transformative topic? We'd love to hear your ideas, questions, or insights in the comments section below. Your perspective matters, and we're excited to spark a conversation about the future of energy. Don't forget to hit that subscribe button to stay updated on the latest in-depth analyses of cutting-edge technology, national strategies, and groundbreaking innovations that are shaping the world's future. Top 10 Discoveries. Official will return with more captivating, untold stories, ambitious projects that push the boundaries of what's possible, and quiet revolutions with profound global impact. We can't wait to see you in our next video.